So let me say a few things before I start lecturing. So obviously the tests were just taken, so I don't have the grades yet, but when I do, I'm going to obviously update all your averages. But I also put what you need approximately in test 4 to get an A, B, and C in the class. I do this, most semesters. The formula, anyhow, it doesn't matter on your end, but the formula is a little bit different this semester because of the homework being different. But anyhow, I'll figure that out and post that after I get the test back from test 3. The other thing I want to say is that I posted the flip video. I'm going to go over that quickly today. If you want a detailed explanation of what I'm going to do at the start of class, you can watch the flip video. I'm just going to go over the highlights of what we talked about in the flip video, which is basically RLC circuits. So you should watch the flip video and look at the notes as well. Tomorrow, I'm actually going to post the last homework. I mentioned it, I think on Saturday or something. I don't remember when, but sometime. And so it's going to be more questions than normal, but it's also going to be worth more points than normal. And you have until the following Friday to do it. So tomorrow, basically after it's posted, I'm going to have a review session on basically, how to do it a couple hours after I post it probably. And the Wednesday after, I'll probably have a little review session, not as long as the one tomorrow, just to see if anyone has any extra questions on the homework. And then, it's through that Friday. Basically, we have a week and a half to do it. So hopefully everyone will get a perfect score on the homework since it's worth more points than typical. The other thing I want to say is there's going to be one more quiz. I mentioned more about the quiz on Thursday, but there'll be one more quiz. And so the next test is basically 2 weeks from this Thursday, right? So this week's sort of a normal week, except the fact that the homework's posted on Wednesday instead of Friday. Besides that, it's a normal week. But then next week, so normally we do, things the week before the test, we do material for the next test, right? So this happened also last semester, last semester. The question is, what do we do the week before the test, since it's normally on another test? So what we do next week, since there's not going to be a homework on it, it's not like it's unimportant material, but just I won't have time to give you homework on it, give you a quiz on it. So what we do next week is going to be extra credit on the quiz, right? So basically, it's not on the quiz, sorry, on the test is what I meant to say. So on the last test is going to be, I do this every semester, by the way, it's not unusual, but on the last test, there'll be more extra credit questions than just the one that's related to the video, and will be related to what we do next week, right? So basically what I'm trying to say is that the next test is more than 108 or 110 points, right? So a typical test is 110 if you get everything right, test 1 through 3. But test 4 actually be more than 110. Plus you have the homework, which is going to be more than kind of typical homework, as you'll see when I post it tomorrow. So there's like one last Hail Mary is what I'm trying to say for those who aren't doing well and for those who are. It doesn't really matter, but for those who need some extra points in the last bit of the semester, that's the point of what's going on for the 4th test and the last homework and the last quiz too, which I'll go over again, like I said, later on. So does anyone have any questions on that? It'll be a little bit strange on the review tomorrow because the homework covers what we did since last test and what we're doing this week. And of course, tomorrow is before Thursday. So anyhow, I'll go through the homework, but there'll be a couple questions on the homework we won't see the explanation of until Thursday, but I'll still go over it on Wednesday and then I'll go over it more thoroughly on Thursday, the theory behind it, right? I'll just show you the mechanics of how to do the problem on Wednesday. Okay, so let me just go over the flip stuff quick. Like I said, if you want a better explanation of what I'm about to go over, watch the flip video because it's it's a typical sort of pace that a typical class goes at because it is from another class. But let me just summarize how this works. for these things called RL circuits. So basically, if you put a resistor, an inductor, and a capacitor into an AC circuit, so this is not like a normal battery, like a voltage coming from a generator or something, where the current's constantly sort of changing directions. The resistor basically isn't really affected by that. It just, whatever the voltage is doing, the current does through the resistor. I mean, you have Ohm's law, right? So basically, the current through the resistor is the voltage divided by the resistance, if that was the only thing in there. So if the voltage changes direction, the current changes direction through the resistor, but nothing really happens to it. You can still use Ohm's law. The only difference for the resistor is that the voltage is constantly changing. So at a certain time, the voltage will be some amount, and then you just divide it by the resistance, and that gives you the current through the resistor. Anyway, the point is, nothing much happens with the resistor in an AC circuit. However, the inductor and capacitor are affected by an AC source because when you change the frequency, or basically how often you can think of the current turning on and off, which is related to the frequency of the source here. It's like a generator. If you spin at a certain frequency, the current changes at that same frequency. Anyhow, it changes the flux through the inductor quicker, which affects the inductor, because that's how inductors work. They work on flux. So what I'm trying to say is that the inductor is affected by frequency. It's not like the resistor. Same thing for capacitors, because capacitors need time to charge. So basically, the longer you leave the circuit on for, or the smaller the frequency, the larger the period, then the capacitor can charge all the way, and then it can discharge all the way, and then it can charge all the way and discharge. If you increase the frequency, it can't charge. You can't get up to full charge is basically what I'm trying to say. So anyhow, the point is the inductor and capacitor are affected by frequency. That's the most important thing to understand for these AC circuits. If you put an inductor and a capacitor in an AC circuit, they're affected by frequency. So what you can do is you can talk about the resonant frequency of a circuit. Okay, so let me go to here. So you have these two things here called XL and XC. So XL is the sort of like the resistance of an inductor in an AC circuit, and XC is the sort of like the capacitance, the resistance of a capacitor in an AC circuit. These are called reactances. You have inductive reactance, which is XL, and capacitive reactance, which is XC. So, like I said, I go over into detail on the video, but XL is equal to 2 pi FL. So basically, F is the frequency of the source. It's basically how often the voltage source is turning on and off, basically, right? So that's controlled by the source. So anyhow, but you have this equation for XL. It'll be on your equation sheet. You'll see it again in this example in a minute. But it's 2 pi FL. So basically, you take 2 pi, you multiply by the frequency of the source, and you multiply it by the inductance, and that gives you some thing called XL, which is measured in ohms, and it's kind of like the resistance of an inductor in an AC circuit, right? And then you have this thing called XC, which is the capacitive reactance, which is 1 over 2 pi FC, which you'll see in a minute in the notes, and it's also going to be on your equation sheet. But anyhow, so you plug in the frequency and the capacitance into that equation, you get the what's known as the capacitive reactance. It's like the resistance of the capacitor in an AC circuit. But they're inversely related to one another. So basically, XL is related to frequency because it's inversely related to frequency. It's 2 pi FL. So basically, if you increase the frequency, the sort of resistance of the inductor goes up, and it limits the current in the circuit, right? Because the resistance goes up. You can think about it like that. But XC is 1 over 2 pi FC, so the F is in the bottom, right? So basically, they're inverse related, right? So basically, that means the smaller the frequency, the bigger the XC, which means the bigger the resistance and the less current you have in the circuit. So basically, the inductor's trying to kill the current at high frequencies, and the capacitor is trying to kill the current at low frequencies. That's basically how it works. And then in between, they're at some frequency they equal one another, and that's when you get the most sort of current in your circuit, and that's at the resonant frequency, which is this question here. So there's an equation for the resonant frequency. You just said the capacitor reactance equal to the inductive reactance, and you solve for the frequency, and it gives you this equation here to be on your equation sheet. So basically, if you know the value of the inductor in your circuit and the value of the capacitor in your circuit, You plug it into this equation, and that'll give you the resonant frequency of your circuit, which is where you get the most current, because everything sort of balances out at this frequency. If you go to a higher frequency, you have less current in your circuit due to the inductor. If you go to a lower frequency, you also have less current due to the capacitor. This is when they sort of balance out, right? Okay, so this is one of the things you can calculate for an RLC circuit, the resonant frequency. And then you can calculate the maximum current at any frequency, particularly the resonant frequency. You can figure out the maximum current. So the maximum current, so basically the voltage source is constantly changing all the time. But it goes from 0 to some maximum value, and then it goes to 0, and then to a negative maximum value, and then back to 0, and then to another maximum value. So all we're focusing on for these RLC circuits is what is the maximum current, right? So the current changes too all the time. So what we're trying to do is just find the maximum of it, because that's the most important thing to figure out. So to find the maximum of the current, you take this equation. It's like an Ohm's law equation. I'll explain what this thing is in a minute, but it's V max is equal to I max times Z, right? So it's basically like V is equal to IR, right? It's the same thing. Except you have a Z here, and Z is equal to this thing called impedance, which I'll show you what that is in a minute. But there's one conceptual thing to understand is that at the resonant frequency, right? So basically, you have this thing called the resonant frequency, which for this circuit is 1591.55 hertz. That's just the value you get when you plug in the inductor and the capacitor. So basically, you can adjust the frequency of the voltage source, which is basically how often it goes on and off, more or less. And if you tune it so it's exactly this frequency, then the impedance, this thing called Z, which I'll explain a little bit, explain this in more detail in a second. But this thing called impedance is equal to the resistance only at the resonant frequency. So basically, if you want to find the maximum current at the resonant frequency, which is something you could be asked, you just take the maximum voltage of your voltage source, which is basically given most of the time, and divide it by the value of a resistor. It's basically just Ohm's law, right? But that's only at the resonant frequency. If you're at any other frequency besides the resonant frequency, which is this part here, you have to figure out the total impedance, which is this thing called Z. So this thing called Z is the total impedance of the circuit. So basically, it's like the total resistance of the circuit, of an AC circuit, but it's not called resistance because resistance is only for resistors. Right? We can't call it resistance, so we call this thing called impedance. But basically, it's like the total resistance of everything in your circuit, right? So it's given by this equation here, which would be on your equation sheet. So it's equal to the square of the resistance plus the square of the difference of the reactances at that frequency, and then square root, and that gives you this thing called impedance. So like I said, this is how you calculate, this is how you calculate the inductive reactance. It's called the XL thing. It's just 2 pi FL, right? So if you had some frequency, you just plug in that frequency and the value of the inductor, and that gives you this thing called XL, which is measured at ohms. And then XC is 1 over 2 pi FC, as you can see there. So you plug in the frequency and C, and that gives you XC, which is also measured in ohms. And then you plug them into this equation, and that gives you your total impedance for the entire circuit at any frequency. Now, this is why the impedance is equal to the resistance at the resonant frequency. Because at the resonant frequency, this is something you should know, and I went over it, in the flip video, I think more than once. XL and XC are the same value at the resonant frequency. That's how you find the resonant frequency. So when XL and XC are the same, they just cancel out and you get the resistance, right? That only happens at the resonant frequency, though. At any other frequency, these two things will not be the same, so they don't cancel out. So it's not going to be the resistance at any other frequency. It's always going to be bigger than the resistance because you're adding something to R squared here, right? Okay, so that gives you the impedance at some frequency, and then you use this equation, like I said. This is the general equation, I max times Z is equal to V max, so that gives you the maximum current at any other frequency. You have to find the impedance, and then use this equation, and that gives you the maximum current. So it's less than the current at the resonant frequency, it's 1 amp. And then at this frequency, it's less than that. At any other frequency, it's going to be less than the resonant frequency. The current's going to be less than the resonant frequency. Then the other thing you can figure out is the phase angle. So it turns out that, so you have the voltage doing something. It looks like a sine wave, and you have the current doing something. And if you have an inductor and a capacitor in your circuit, in general, they're not going to be lined up with one another. In other words, if you look at their maximums, they're going to be shifted, not lined up. And this is called the phase angle, the difference between their two peaks, right? And this is how you find it. It's just using this equation, XL minus XC divided by R at whatever frequency you're talking about. And then you take the inverse tangent of that, and that gives you some angle, which is the phase angle. So the phase angle could be positive. It could also be negative. It doesn't really matter if it's positive or negative. This is just how you calculate it. But at the resonant frequency, you see XL and XC are the same thing. So this becomes 0. And the inverse tangent of 0 is 0. So basically, at the resonant frequency, they're basically lined up with one another, right? So at this one specific frequency, the peak of the voltage is lined up with the peak of the current, right? That's what that means. But at any other frequency, they're not going to be lined up, right? So this is, there's graphs about this in the PowerPoint. Oh, I got to post the PowerPoint. I just realized that. I forget to post the PowerPoint. But I'm going to post it today to go along with the flip video. And then the other thing you can talk about is this thing called the RMS value for the voltage. It's just a very simple thing. So basically, you can characterize something by the maximum value, and then this thing called a root mean squared value, which is basically like an average value. It's not really an average, but it's sort of like an average value of the voltage or whatever. And so this VRMS thing is just the maximum voltage divided by the square root of 2. That's all it is. You just take the maximum voltage and you divide it by the square root of 2, and that's how you find the RMS voltage. So this, I gave you the RMS voltage instead of the maximum voltage, but it's basically the same thing. They're related very simply to one another. So at the resonant frequency, once again, the impedance is equal to the resistance. So how does the V equals IZ equation change if you have RMS values? It doesn't change because the square root of 2 sort of cancels out on both sides. So you have the same equation. So in other words, if they're both maximum values, you can use this equation. If they're both RMS values, it's basically the same equation. Sorry, choking for some reason. Okay, so what was I saying? Okay, so if they're both maximum values, you can use this equation, right? If they're both RMS values, you can use this equation. However, if one of them is an RMS value and one of them is a maximum value, you have to make them both the same thing, right? You have to make them both maximum values or make them both RMS values, right? But it's simple. I mean, you just take the maximum value divided by the square root of 2. That gives you the RMS value, right? It's not really a big thing. But they both have to be the same quantity. You can't have two different things there, right? Okay, so that's how that equation works. Once again, the resonant frequency is what we did in the last problem. Once again, if you go to some other frequency other than the resonant frequency, you have to figure out what the new value of XL and XC are to find the impedance. And then once you find the impedance, you can use that to find the current, or in this case, the RMS current at that frequency. And the phase angle, same thing. And this is new. We did in this example here. There's two other things you can find with RLC circuit, which is called the power factor, which is a very easy thing to figure out. All you do is take the phase angle, find the phase angle, which is using this equation here, and then take the cosine of it, and that gives you what's this thing known as the power factor. The power factor is 1 if you're at the resonant frequency. That's why it's called the power factor, because you have the most power produced in your circuit when you're at the resonant frequency, because you get 1. At any other frequency, it's going to be less than 1. That's why they call it a power factor. And the other thing you can figure out is the average power of an RLC circuit. So it's two different equations. This is the RMS equation. It's RMS VRMS times the cosine of phi. There's also one for the maximum values. If you're using maximum values, both of these will be on your equation sheet, but it's 1/2 I max V max times the cosine. There's a 1/2 in front of it if they're maximum values. However, if they're RMS values, it's just this equation. So basically what you do is you calculate the IRMS at this frequency, which is what we did here, right? It's this thing. Then you multiply it by VRMS, which is basically given, right? That's given here. And then you multiply it times the cosine of the phase angle, which is what's called the power factor. And that gives you the average power. So that's the main things for an RLC circuit. So the main things for an RLC circuit, once again, you can watch the flip video if you want a better explanation, is to know what inductive reactance is, what capacitive reactance is, how they're both affected by frequency, how to find the total impedance, how to find the resonant frequency, how to find what happens at the resonant frequency. So the impedance is equal to the resistance at the resonant frequency. The phase angle is 0 at the resonant frequency. The power factor is 1 at the resonant frequency. You have the most current at the resonant frequency. And then know how to find the phase angle when you're not at the resonant frequency, the maximum current or the RMS current when you're not at the resonant frequency, and the average power. Right? Those are the main things you should know for these RLC circuits. Right? Like I said, that was a quick run through, right? If you want a better explanation, watch the flip video, right? It goes through it much slower. All right, so does anyone have any questions on the RLC circuits or AC circuits, basically? Actually, not too bad. It looks hard, but it's not so bad. There's only a couple main points, and then if you understand those main points, it's actually fairly straightforward. Okay, so then what we're going to do today is move on to the next topic, which I'll post this PowerPoint today, along with the AC circuit one, RLC circuits, because I just forgot to post it. I just realized that this morning. But I'll post both of them today. And that is, we're going to start with this lecture, and we'll finish it on Thursday, which has to do with electromagnetic waves and geometric optics. So you understand why it's really geometric optics. I don't know why I put geometrical. Anyhow, it doesn't matter. Geometric optics and electromagnetic waves. So the first thing I'm going to talk about is just talk about what an electromagnetic wave is first, and then we'll move on to optics after we're through talking about electromagnetic waves. So, so it's a little bit hard to understand because really, I mean, honestly, to really understand how electromagnetic waves are produced, you really need a really high level of math to figure this stuff out, you know, to get all the details of actually how this works. But you can get a general sense of how it works just by this sort of explanation. Okay, so suppose you have a antenna. Okay, so this thing might seem confusing, but antenna is basically just a current that goes up and down in a wire, right? So you have a current. So you have these electrons going up and down in this wire. That's basically what an antenna is. Okay, so when electrons go up and down, they produce two things. They produce a current, which produces a magnetic field, and they also produce electric field, because any charge produces electric field, correct? But the point is, if you have electrons going up and down, they also produce a current, and because they produce a current, they produce a magnetic field. Basically, any moving charge produces a magnetic field. So we're going to focus on it like it's a current. So when this, say electron goes up and down like this, right? So the current's going back and forth like this. So this is what you had on your last test, right? Which I hope you basically understood. So if the current's going one way, there's going to be a magnetic field, you know, that curls around by the right-hand rule, maybe going in this direction here, right? If it's going up, right? If this current's going up, you have the magnetic field loops going around like this. If it's going down, it's going the other way. Anyhow, so the point is, if the current goes one way, so imagine the current just going up and down, up and down, up and down. So the magnetic field's got to go one way, then it's got to go the other way. Then it's got to go one way, then it's got to go the other way, right? As the thing goes up and down. So that's this shaded part of this thing, electromagnetic wave, which I'll explain in a minute. But then there's got to be electric field too, because if you look at one charge going up and down, you have electric field basically following it as it goes up and down, right? Remember, electric fields, I mean, for negative charges, these are electrons. They go like straight towards the charge, right? So basically, if you watch one electron, right, there's got to be electric field going towards it, but it's got to follow it going up and down like this, right? Okay, so there's got to be an electric field sort of produced by this electron, and there's got to be a magnetic field produced by the current the electron produces. And they're going to be, like I said, the details are really hard to understand, but you get the general sense of what's going on here. You have electric field going, say, in this direction here, like in the x direction, and you have a magnetic field going, say, in the depends what the, say if this is the y direction, it would be like the z direction, right? And that produces this thing called electromagnetic wave. So it's a combination of electric field produced by these charges going up and down. Basically, a moving charge produces this electromagnetic wave. So it's a combination of electric field, which is this thing here, this part here, and this magnetic field, which goes like this, right? So that's why it's called electromagnetic wave, right? Or the EM wave for short, right? So basically, any moving charge produces this thing called this electromagnetic wave. Now, as this charge moves up and down, the wave actually moves in this direction, right? This whole weird-looking wave, which I'll show you in the next slide, it's more clear exactly what's going on, moves in a certain direction. And that's given by one simple right-hand rule. It's the only right-hand rule, by the way, on test 4. So to understand how this right-hand rule works, but you've had practice from the last test, and like I said, there's only one right-hand rule on this one. Basically, you point your fingers in the direction of electric field at a moment of time. So like you pick this time here, like this time here, and you point your fingers in the direction of electric field. I'll explain on the next slide. It's a little bit easier to just see it on the next slide. And you face your palm in the direction of the magnetic field. So your fingers point in the direction of the electric field. Your palm faces the direction of the magnetic field. And then whatever your thumb points gives you the direction of the velocity or which way the electromagnetic wave is moving. So it works like, here's a GIF, or GIF, I don't know how you say it, but I say GIF, of a electromagnetic wave. So basically you have this charge moving up and down, and because the charge is moving, it produces a magnetic field, and it always has electric field there. So the red is the electric field, and the blue is the magnetic field. So if you look at this right-hand rule, right, you point your fingers in the direction of the electric field and your palm in the direction of the magnetic field. So the red, I think, is the electric field. So let's look at this case here, right? The red is basically going towards the ceiling, see, basically in the positive z direction. So you point your fingers in the positive z direction, and your palm is facing in the direction of the magnetic field, which in this case is the positive x direction. See, the blue is facing positive x, right? So you face your fingers towards the ceiling, and you face your palm in the positive x direction, which is towards the right, right? Fingers towards the ceiling, palm to your right, and your thumb points away from you, right, in the positive y direction, right? And that's the way this thing is moving. It's a little bit hard to see, but this is the z direction, this is the x direction, and this direction that it's moving is the positive y direction, right? So that's how you do it, right? Your fingers in the direction of electric field, palm in the direction of magnetic field, and your thumb points in the direction of the which way the wave is moving, right? For this case, it's positive y. Okay, so that's the only right-hand rule, though, on the test, right? And I'll just say, you know, on a quiz or a test, I'll say the electric field's in the x direction, the magnetic field's in the z direction, what direction is it moving, right? So you just need to know that right-hand rule. Okay, so electromagnetic waves also move at a certain speed in a vacuum. We're going to talk about what happens when they move through things that aren't a vacuum in a bit when we get to refraction. But for now, let's just talk about waves moving through a vacuum, or basically through air. So it's basically the same thing as through air, too. So through a vacuum, these electromagnetic waves, which are produced by moving charges, are basically always move at the same speed, which is 3 times 10 to the 8th meters per second, which is the speed of light. Right? So 3 times 10 to the 8th meters per second is pretty fast, which I'll get to in a minute. In fact, it's nothing, as we know, as we currently know, can go faster than the speed of light, although there's sort of ways around that. But you're not really going faster than the speed of light. You're currently going faster than the speed of light. You can't actually go faster than the speed of light. It's also related to the 2 constants that we've been talking about sort of often, although one of them we didn't mention as much as the other one. So this wave is made of electric field and magnetic field. So you might think how light moves is related to both electric and magnetic fields, and it is. Specifically, the speed of light is given by this equation, 1 over the square root of epsilon naught mu naught. So mu 0 is the thing we used all the time for calculating magnetic fields in last test. It's associated with magnetic fields. Epsilon zero we use a little bit. We use it for capacitance and things like this, but you got to remember epsilon zero is related to K, and we use K for electric field and electric force calculations. So the two fundamental constants of electric fields and magnetic fields are related to how fast light moves. So anyway, if you put in these numbers into this equation, you'll get 3 times 10 to the 8 meters per second as your answer for the speed of light. Okay, so something that that comes up every once in a while, it's kind of important to know, is that the concept of light year. So the term year is in the term light year, and of course, year is a measure of time. So some people think that a light year is some measure of time, and yeah, so it's just how much science fiction you watch or whatever. But it's not a measure of time. It's a measure of distance, right? A light year is a measure of distance. It's basically how far light travels in a vacuum in a year. That's what a light year is. So you take how fast light moves in a vacuum and you multiply it by how many days there are in a year, how many hours there are in a day, and how many seconds there are in an hour. And that gives you pretty much what a light year is, although there isn't exactly 365 days in a year. It's a little bit more than that, which is why I have a leap year every 4 years. But nonetheless, this is a pretty close estimation of what a light year is. So 1 light year is 9.48 times 10 to the 15 meters, which makes more sense in kilometers, 9.46 times 10 to the 12 kilometers, which is 9.46 trillion kilometers, which is a pretty far distance. In terms of miles, by the way, it's about 6 trillion miles, about a little bit less than 6 trillion miles, right? Because we know miles more than we know kilometers. But 6 trillion miles is pretty far distance, right? This is why astronomers measure things in light years, because it doesn't make sense to measure things in miles. I mean, it doesn't make any sense at all. The nearest star is about 4.2 light years away. That's the closest thing to us outside of our solar system. So even that's pretty far by our standards. The Milky Way, our galaxy that we live in, is about 100,000 light years across. And the visible universe that we can see is something about 93 billion light years across, which is pretty amazingly big. You can't even sort of conceptualize these numbers in your head, but anyhow, a light year is a pretty large distance, right? And actually, when you start getting into astronomy, you actually use things like parsecs, which are multiples of light years, right? So it doesn't even make sense to use light years when you're talking about things across the, something across the other side of the universe. But anyhow, so sort of interesting concept related to light is that how fast light moves is that it's not that it's finite. It's not infinite. In other words, it doesn't take light an instantaneous amount of time to travel from place to place. It's delayed, right? So basically, if the closest star is 4 light years away, which it is, it takes 4.2 years for this starlight to reach the Earth, right? So what we're seeing is light that's 4.2 years old, right? So, I mean, theoretically, it's not going to happen anytime soon, but theoretically, in our current time, the star could have exploded already, or it's exploding right now, but you wouldn't know it exploded until 4.2 years later, right? Because it's 4.2 years delayed. So this is why we're always making bigger telescopes, basically. It's to see further and further and throughout the farther into space. So the bigger the telescope, or if we put a telescope in space like Hubble, you can see farther and farther away, but when you're seeing farther and farther away, you're actually seeing backwards in time, right? It's kind of weird when you think about it. So, there are things that we can see which are, this is Hubble's deep field. This is actually an old image now. They have updated images, but anyhow, each one of these little dots is a galaxy from Hubble, and some of these things are like 12 billion light years away, which is pretty far. And it's amazing we can even see 12 billion light years away, but we can. So basically you're looking at the universe as it was 12 billion years ago. And the universe is only like about 15 billion years old. So you're looking at a universe that's only a few billion years old at the time, right? So you can understand how the universe evolves if you learned farther back in space, right? That's why we build these telescopes the way we do. So that's kind of interesting if you think about it. Okay, so let's get back to the physics of these electromagnetic waves. So basically, let's go back here for a second here. So typically how an electromagnetic wave is made is you basically have an oscillating charge, right? So it's basically oscillating up and down at some frequency. In other words, the time it takes to go, back and forth once is called the period, right? So, okay, so you start your watch there, and then you wait for it to come back again, and that's called the period, right? The time it takes to repeat itself once. Related to the period is the frequency, which is the inverse of the period. It's how many times per second it goes up and down. Anyhow, the frequency that this thing is oscillating is equal to the frequency of the electromagnetic wave. So basically, the electromagnetic wave has a certain frequency too. It's related to the frequency of the charge, right? So basically, these waves have these things called frequencies associated with them in periods, right? And the thing that they also have is the wavelength, right? So basically, if you look at the distance between two like peaks, like say red to red here, there's a certain distance between them, which is the wavelength of this electromagnetic wave. So all these things are related to one another. The speed of the wavelength of the wave, and the frequency of the wave are related to one another, just as they are for sound. We did the same thing for sound waves at the end of Physics 1. So this is the equation that relates the period of the wave to the frequency. And then, well, you do some physics. I mean, it's the same explanation as what I did in Physics 1 if you took Physics 1 with me. But you can also relate how fast the wave is moving to its wavelength and frequency through this sort of simple equation here. So basically, if a wave is traveling, electromagnetic wave that is traveling through a vacuum, it's moving at the speed of c, right, the speed of light, which is 3 times 10 to the 8th meters per second. And that's equal to the wavelength times the frequency, right? The wavelength, which is basically how far the peaks are apart, times the frequency, which is related to basically how fast the charge is shaking. So basically, if you're talking about light moving in a vacuum, this is always constant. It's always the same number, 3 times 10 to the 8th meters per second. So that means that the wavelength and frequency are inversely related to one another. If you solve for the wavelength, it's c over f, but that c is always the same number. So basically, it's inversely related to f. If you make the frequency bigger, you shake the charge faster. The wavelength is smaller, right, because it's inversely related to one another. If you shake the charge slower, then the wavelength gets bigger. You have a bigger wavelength, electromagnetic wave. So let's just do a simple example with wavelength, because this is it's a pretty simple equation, and it is simple, but it comes up sort of often. Actually, I forgot. We're going to do a right-hand rule example and then a wavelength example. I forgot to do the right-hand rule example. I forgot I have right-hand rules. Okay, so let's just do those quick, and then you can probably take your break after we do these examples. Okay, so I'm going to go back to the right-hand rule quick, and then we'll do a quick example with wavelength. Okay, so let's do this. At one moment of time, an electromagnetic wave, which is what we're talking about now, has an electric field in the positive x direction and a magnetic field in the positive z direction. Okay, so what direction is the electromagnetic wave moving? You can also say what direction is it propagating. It's a typical sort of terminology, but I'm just going to say moving. Propagating is the same thing as moving, in case it comes up later on. Okay, so you just got to do the right-hand rule here. So basically, the electric field is your fingers, and the palm is the magnetic field. So you face your fingers in the direction of the electric field, which is positive x, so to the right, and you face your palm in the direction of the magnetic field, which is towards the ceiling, which is positive z, right? And whatever way your thumb points gives you the direction of the which way the wave is moving. which is towards you, should be towards you, right? Your thumb should be pointing towards you. So towards you is negative y, right? All right, so that's that one. We'll do one more. It's pretty straightforward, though. If an electromagnetic wave is moving in the positive x direction, what is one? So there's actually an infinite amount of answers. We're just going to do the simplest one, although there is more than one answer for this one. I'll tell you why there's an infinite, actually, number of answers. But we're going to do, like, sort of the most straightforward one. Okay, so if electromagnetic waves moving in the positive x direction, what is one possible combination of directions of electromagnetic fields? Okay, so your thumb is the direction of the, which way the wave is moving. So you point your thumb towards the right, right? In any way your hand faces, so your thumb is pointing to the right, is a possible answer. So, you know, all these sort of things you can do with your hand, right? As long as your thumb points to the right. But the easiest way to do is just pulling your hand out, right? Like this, with your palm facing up, with your thumb pointing to the right. So in this case here, what would the direction of the electric field be if you just point yours? So the electric field's your fingers, but you're pointing away from you, right? So it's positive y. And your palm is pointing up towards the ceiling, which is positive z, right? So that's one combination. You can also do this, point your hands towards you. There's all sorts of things you can do, but this is the easiest way to do it. Just point your hand out from you. So by the right-hand rule, one combination is the electric field. And what do we say? Positive y, right? And the magnetic field and the positive z, right? So that's one, but there's more than one, right? Obviously, as I just explained. Okay, so that's the right-hand rule. Those are the questions will be written for the quiz and test. Pretty straightforward. You just need to know that one right-hand rule. And now we're going to do a quick example with wavelength for magnetic fields. And then you can take your break. I'm just going to box these answers, and then I'll go on to the next example. But the next example is pretty straightforward. It should only take like a couple minutes, hopefully. Okay, so let's do the next example. All right, so an electromagnetic wave in a vacuum has a frequency of, okay, so typically the frequency of electromagnetic waves are pretty big. So that's megahertz, right? So this is a typical frequency, kilohertz, megahertz. Kilohertz is pretty straightforward to understand, but megahertz, we don't see the prefix M, capital M, that often. We see little m, which means milli, but this is capital M, which actually means mega. So we have to understand what mega means. But besides that, it's pretty easy. The hardest thing is understanding what M, capital M means. What is its wavelength? Okay, so this capital M, like I said, is mega. And mega is a million, so it's 10 to the 6th, right? That's what a megahertz is, right? You have to convert to hertz. You can't use just megahertz. But besides that, it's pretty straightforward. Hold on, I'm getting a call. I need to turn that off. Okay, so you have this basic equation, right? If it's moving in a vacuum, then it's moving at the speed of c, and c is equal to the wavelength times frequency. So basically, if you want to find the wavelength, like I said, this equation is pretty straightforward, but it does come up often when you're doing optics and electromagnetic waves. So it's good to see how you do this once. But it's just 3 times 10 to the 8th, which is a constant, which will be on your equation sheet, the speed of light. Just like mu0 was and k was for the other tests. And then you divide by the frequency, but it has to be in hertz. So this is, omega is 10 to the 6th. right? That's how you convert, right? So typical frequencies are kilohertz, megahertz, sometimes gigahertz. Gigahertz is 10 to the 9, but the most common ones is kilohertz and megahertz for frequencies of electromagnetic waves. So you get 150 meters actually. So it's actually pretty large, right? So basically, a frequency of 2 megahertz produces a wavelength of 150 meters, right, for these electromagnetic waves. So like I said, this equation is pretty easy. You just got to know the prefixes for the hertz, right, to convert to them. Okay, so take a 10-minute break. When you come back, we'll do other things related to electromagnetic waves. Hopefully get through a chunk of this today so that the homework problems I explained yesterday, tomorrow won't be so mysterious, but we'll see how far we get. So let me go back to the PowerPoint. If I can get back to it. Okay, so related to frequency and wavelength is something else we can talk about that's sort of conceptual, which is known as the electromagnetic spectrum. So basically, let me go back to this picture once again of how the electromagnetic wave is made. Just pay attention to this charge going up and down, right? So you can shake this charge however you want, right? And that basically controls the frequency of the wave, because the faster the charge goes up and down, or the higher the frequency, the quicker you move that thing up and down, that makes the frequency of the electromagnetic wave bigger. If you shake it up and down slower, that makes the frequency slower. So what I'm trying to say is there's no limit, basically, to how fast you can shake this thing or how slow you can shake it. And that leads to what's known as a spectrum of frequencies and also wavelengths, because wavelengths and frequencies are basically related to one another for waves moving in a vacuum. So it goes like this. This is the electromagnetic spectrum here, right? Shaking charges at different frequencies produces this thing called electromagnetic spectrum. So this is hard for me to read here. Okay, so on the right-hand side you have wavelength. On the left-hand side you have frequency. So, okay, so the bottom here is low frequency, and then if you go up here, you go up to higher and higher frequencies. But frequency and wavelength are inversely related to one another. I just went over that, right? We just did an equation with it. So when you look at the wavelength, you can either look at it in terms of frequency or wavelength, because they're basically just related to one another by that simple equation, C equals lambda f. But if you go higher in frequency, that actually goes smaller in wavelength, right? Because they're inversely related. So this goes from small wavelength up here to a long wavelength down here, or a big wavelength down there. Okay, so let's just focus on frequency though, because that's, focusing on one is good enough. If you understand one, you basically understand the low one, the other one. So at low frequencies, you have what's known as long wavelength electromagnetic waves, because for low frequency, you have long wavelengths. And it's pretty straightforward. If you shake the charge a little bit faster, then you get into radio waves. So this is how radio and TV waves are broadcast in some sense, although now they're digital, but they're still broadcast at some, encoded at some frequency. So obviously we can't see radio waves, but they're just electromagnetic waves that we use to send data, basically. And then if you shake the waves, the charges faster, and you go to a higher frequency, then you get to microwaves. These are the same microwaves which, are in your microwave oven, which basically oscillate molecules in your food to make them hot. But anyhow, it's the same microwaves. Obviously, you can't see microwaves in your oven. I mean, when you press the button, the light goes on, but those aren't microwaves. You can't see the microwave. That's from the light bulb in the microwave. And then if you shake a little bit faster, you get to infrared. And infrared light, or electromagnetic waves, is basically something we can't see, but it's basically heat, right? So basically, heat produces electromagnetic waves, right? So basically, if you want to see heat, you develop something that senses infrared. And then you shake faster and you get to visible light. So this is light that we can see. But all this light is the same thing. It's just shaking charges at different frequencies for some reason, probably due to the sun. If you shake a charge at a specific frequency, we can see it, and we see it as color, right? So this small little part of the electromagnetic spectrum is what we can see. If you expand it, it goes like this. The lowest frequency that we can see is red light. And then if you shake faster and faster, it goes to orange, yellow, green, light blue, blue, and purple, right? So purple is the highest frequency of light we can see. Although typically, for some reason, I don't quite know why, they always say blue. Blue is up there, but actually violet is the highest frequency, right, that we can see, right? It goes all the way to violet. So this is also, how if you look at a rainbow, the colors are dispersed. It's no coincidence. It's related to the frequencies. They get sorted out in a certain way for a rainbow. And then if you shake higher, you get ultraviolet, right? So that's higher than violet. That's why they call it ultraviolet. We can't see ultraviolet, although bees can see ultraviolet. We can't see ultraviolet. And then if you shake faster, you get to X-rays, which is X-rays. I mean, that's what, when you need an X-ray done, this is what they use at the hospital. And if you shake higher than that, you get into the highest frequency, which is lumped into this thing called gamma rays, which are the highest frequency electromagnetic waves that basically we've seen so far. But the main point is that all of these things are the same thing. It's just shaking a charge faster or slower produces all these different sorts of electromagnetic waves, and only a certain portion of them we can see, right? We evolved to see this part. It's actually a very small part. It's just this little chunk of electromagnetic wave. In other words, most things going on in nature we can't see visibly with our eyes. You can detect it with other instruments, but we cannot see it with our eyes. So it's just something interesting too to point out, because when you just go out walking around, there are radio waves passing around you. There's infrared from heat. There's ultraviolet from the sun. There's X-rays coming from the sun. And you don't see any of it. You only see a little small portion of it, right? So basically, if you want to see what's going on with the universe, you need to build these other things which can detect all these other electromagnetic waves besides the visible waves. Okay, so I'll have a video to play related to this probably on Thursday, sort of an additional video, not the extra credit video, a short little video. But I want to get through as much as the PowerPoint today as possible so I can explain the problems tomorrow. Another thing you can talk about is this thing called the Doppler shift, that basically happens to any wave that's moving. So sound Doppler shifts, and I actually did Doppler shift for sound, but also electromagnetic waves Doppler shift. So basically whenever you have a wave that's moving, or something that's producing a wave, and it's moving, be it a water wave or a sound wave, in this case electromagnetic wave, it undergoes this thing called a Doppler shift, which I'll explain in a minute. So basically, I already went through this explanation in Physics 1, for those having Physics 1, but it's the same explanation. If you're standing in front of the source, if the source is moving in front of you, so the source is a dot, it's producing these electromagnetic waves, which go out in all directions. And basically, if you're standing in front of that source and it's moving towards you, the waves get bunched up, right? Which means the wavelength decreases, right? Because see the waves, they get all bunched up there. There's the distance between those lines. It gets shorter. So that means the frequency increases when the thing moves towards you. If you stand behind it over here and the thing is moving away from you, the waves spread out, which means the wavelength gets bigger and the frequency decreases because they're inversely related to one another, right? So basically, if you're standing behind something and it's moving away from you, the frequency decreases. If something is moving towards you, then the frequency increases. This happens for all waves, not just the light waves. However, for light waves, it has an interesting implication, which I'll discuss in a minute. So how does it work with light waves? How does it, what are the equations that govern it? So this is the case if you're here and it's moving towards you. This is the equation you use for the frequency. This is the frequency you observe. This is the frequency of the source. So basically, if the source wasn't moving, that's the frequency that you'd see, basically. But if it's moving towards you, then you observe a different frequency, which is given by this FO thing. So it's given by this equation here, V0 plus C over C minus Vs. So V0 is how fast the observer is moving, how fast my dot is moving. Vs is how fast the source is moving. So in this case, it's how fast this dot is moving. And you put all those things in that equation, that gives you the observed frequency. If it's receding, if you're on this side here and it's going away from you, then you use this equation here. This is the frequency you observe. This is the source frequency, as if you were standing still, nothing is moving. Once again, V0 is the speed that you're moving, the observer, the person observing the light, how fast it's moving. And then Vs is how fast the source is moving. So sometimes VO is 0. So this would be the case for this dot here, right? So this dot isn't moving, right? It's moving towards me. So VO would be 0 for that case, and it would reduce to be this equation for the approaching case. If I put my dot here, so it's not moving, and the source is receding or moving away, then if VO is equal to 0, you get this equation here. And you can see from each one of these equations that FO is bigger than FS because it's C divided by C minus Vs, but this is going to be smaller than C because you're subtracting something from C. So mathematically, you get a bigger frequency, right? Because you're dividing by a number less than 1. But here, or dividing by a number less than 1 is what I meant to say. And here, because you're adding something to C, this is going to be bigger than C. You're multiplying by a number less than 1. So the frequency is going to be less than the observed frequency if you're receiving. But, so this works for any wave. But for, say, visible light, right? So look at this portion, right? So if a source is moving towards you, the frequency increases, right? This is what's going on. So remember, as you go up here, frequency is increasing, right? So basically what I'm saying is that if you had a source of light that was red, in other words, if you're not moving, or the source isn't moving, it's just a red light, it would appear to be red, obviously. But if it's moving towards you, which way, how does the color become, do you think? If it starts at red and it's moving towards you, what do you think happens? It goes up here, depending on how fast it's going. It could go to yellow, it could go to green, it goes faster than that, blue, and violet, right? So that's what happens when it's moving towards you. What happens if moving away from you? Say you start with blue light up here and the thing's moving away from you. What happens to the frequency? It decreases, right? So it goes to green and yellow and orange, eventually to red, right? Eventually, if it's going fast enough, you can't see it, actually, because it goes to infrared. But this is what actually happens. It's kind of weird, because it's a weird thing to understand. So a sound wave gets higher in frequency or lower in frequency, which is sort of easy to understand, because you can just hear it. But light actually changes colors if it's visible light, if it's moving towards you or away from you. Now, granted, it has to be going fast. It has to be going somewhat close to the speed of light to see this. This is why we don't see it every day, because most things around us don't go anywhere near the speed of light, which is really fast. However, if things are going close to the speed of light, things will change color, which is kind of interesting. Now, what we're talking about is non-relativistic equations here, right? So if things are going really close to the speed of light, like really close, like 90, 95% of the speed of light, then you have to use relativity, and these equations change slightly. You have to use relativistic Doppler effect. But these equations work pretty well for things that are going, like 70, 80% of the speed of light, 60% of the speed of light. When you start getting 90, 95% of the speed of light, these equations don't work quite as well. But we're not going into relativity here, right? We're just going to use these equations for the Doppler shift. So back to this slide again. So basically, if things are going away from you, which way does it go? It goes towards this direction here, right? Does anyone know what that's called? It's an astronomy term. So basically, if things are going away from you, you get shifted, the color gets shifted down here towards this, which is what? Towards the red, which is known as a red shift, right? Obviously, if things are coming towards you, you get shifted upwards towards the blue. Actually, towards the violet, but everyone says blue. Which is known as a blue shift. But if you know anything about astronomy or interested in cosmology or astronomy, does anyone know, if you look at basically anything outside of our galaxy, basically, are things red-shifted or blue-shifted, or does anyone know? Everything is red-shifted. This is how we figured things, something out about the universe, right? So everything is redshifted. That means that everything is going away from us relative to us, right? So everything is moving away from us. Yeah. You mean, how do we know what a color it originally is? We don't know the directions. I mean, so you can get the directions moving from other sources. But the point is, we just know that it's redshifted, right? That's the main point. And everything is redshifted, right? No matter what direction you look, everything is redshifted around us. Yeah, you're supposed to collide with Andromeda. So basically, yeah, so some local objects are basically, that's not the case, but the overall, if you look at enough data points outside our local sort of neighborhood, everything is redshifted, is what I'm trying to say. So, yeah, that led to the conclusion that there has to be, if you reverse time, then everything is contracted, which led to the notion of the Big Bang, which is basically how we view the universe today, as far as we know, until we see something else that maybe modifies that view, right? That's where it came from. Although a good question is, how do we know it was originally, what color originally was, if we see it here? Does anyone know the answer to that? So suppose something was originally, let's just say, for the sake of argument, something was originally purple, but now we see it as red. All right, that's great. We see it as red, but how do we know it was originally purple? No one knows? No? Atomic spectrum, right? So atomic spectrum we know what colors we're supposed to get from, say, hydrogen. So if you look at hydrogen from some other star that's far away from us, the spectrum of hydrogen shifted. That's how we know. It's the baseline's the spectrum, right? Because we don't know what color originally is, but we do know what colors we should see in hydrogen, right? That's how we get it. Okay, so another application, we're going to do a Doppler shift example in a second, but another example of a Doppler shift or a useful application of Doppler shift is Doppler radar, right? So you always heard the term Doppler radar, whenever you watch the news, right? The weather comes up. What is that? So the question is, what is Doppler radar? Okay, so in a nutshell, this is how it works. Though it's, more complicated than this, right? To understand it exactly is a little bit more complicated than what I'm going to say. But the general idea is this. This is a Doppler radar thing, right? So in the Doppler radar is basically something that spins around all the time. And it sends out this electromagnetic wave, right, of a particular frequency so that it interacts with the clouds the most. I don't know what the frequency is, but some radio frequency. So you don't see it, obviously. It's some invisible sort of frequency. But it sends it out in all directions. And then also in this thing is a detector. So basically it detects the electromagnetic waves that come back. So basically what happens is this. If a cloud is coming towards you, what happens is the wave goes out from the radar, it hits the cloud, and because the cloud's coming towards you, the electromagnetic wave gets Doppler shifted towards blue, right? Because it bounces off the cloud, right? And the cloud's coming towards you. So when it comes back, the frequency that it came back with is a little bit bigger than the frequency it left with. And it can tell you not only that the cloud is moving towards you, it can tell you how fast it's moving towards you because it's related to the speed of the cloud. And it can tell you how far away it is based on how long it takes for the signal to get back and forth. So knowing that, you can figure out if a cloud is moving towards you, if it's moving away from you, how fast it's moving towards you, how fast it's moving away from you, and also where the cloud is, right, relative to the Doppler radar station. That's basically how it works. Okay, so let's do a Doppler shift equation. Example, sorry, I meant to say example. Okay, so like I said, we're doing just the regular Doppler shift. Sometimes you have to use, take into account relativity, but we're not going to take into account relativity for this class, so Sometimes our answers may be a little bit off when we're doing some of these examples, but it's pretty close, even if we're a little bit off. So suppose someone is traveling, so this wouldn't happen, obviously, here, at least not for a while. 6 times 10 to the 7 meters per second. Now, that is crazy fast, right? Nothing even comes close to those, not even rockets being launched into space or even anywhere near this speed. But suppose, we're like 1,000 years in the future, or 10,000 years in the future, and we can go this fast, and I don't know why there'd be traffic lights, but let's just say maybe it's not a traffic light, maybe it's just a yellow light. I don't think you could, sort of regulate traffic with things going this quickly, but it's just a hypothetical. So the question is, what color does the light appear to be? Okay, so, I'll tell you the wavelength of light if you need to know it. But if you just Google the wavelength of yellow light, it's actually, sort of a range of colors, because you have different shades of yellow. You have dark yellow and bright yellow. So it's not just one wavelength, but somewhere in the middle of the sort of spectrum of yellow light, or the different wavelengths of yellow light, a good value is about 600 nanometers. So this is the wavelength of yellow light, right? If you get an electromagnetic wave that has a wavelength of 600 nanometers somehow, you see it as yellow, right? That's just what that means. So a nanometer is typical sort of unit for visible light. And a lot of light is in the nanometer range, which is 10 to the minus 9th. It's basically a billionth of a meter. So it's very small. Right? So the wavelengths are tiny. But if you could somehow get wavelengths to be that tiny for electromagnetic waves, you see it as yellow. Okay, so that's the wavelength. Okay, so for the Doppler effect, it's related to frequency. That's how I spell it out. So basically, what we have to do is find the frequency of yellow light in a vacuum. And the reason why we're doing this is because we need it to put in the Doppler equation, right? This is why we're doing this. So this is another example of using C equals lambda f, right? So that you can always use this equation if you know the wavelength to find the frequency, or vice versa. The frequency is just the speed of light divided by the wavelength. So it's 3 times 10 to the 8th meters per second divided by what a wavelength is, of course, in meters. I lost my 9, but it's 10 to the minus 9. And this gives you the frequency of yellow light. So the frequency of yellow light is 5 times 10 to the 14 hertz, which is pretty fast. In other words, this is 500 trillion hertz, which means you have to shake a charge back 500 trillion times every second. But if you can somehow do that, you produce yellow light, right? So that's what's going on here. Okay, so this is the source frequency. This is the frequency. This is the thing that's producing the light. So it's the source is the yellow light. Okay. So if you're traveling towards the stationary light, right, we're approaching the light, right? So okay, so the equation, the Doppler shift equation, if you're approaching a source of light, is given by this equation here. So this is the frequency you observe. This is what you're going to see. Fs is the frequency of the source, which is what we just figured out. And then it's V0 plus C over C minus Vs. Okay, so V0 is how fast you're moving. Vs is how fast the source is moving. In this case, it's the yellow light, right? The yellow light's the source. So how fast is the source moving? Zero, stationary, right? So this is just 0. So this is V0 plus C divided by C times Fs. So as I said a few times, if c is really close to the speed of light, you'll get, your answer will be a little bit off due to relativity. But this actually isn't that close to the speed of light. It's pretty close, but it's not as close as you need to be. So you get a pretty good answer with this one. So V0 is how fast you're going. So that was what? 6 times 10 to the 7. C is C, so that's 3 times 10 to the 8th. And then you divide by C because Vs is 0. If Vs wasn't 0, in other words, the source was moving also, and then you would put something in for the source, but the source is stationary. So it's just dividing by the speed of light. And you plug that into your calculator, and it shifts a little bit. So it's going to be 6 times 10 to the 14th, which doesn't seem like much, but it's another 100 trillion hertz bigger. And 100 trillion hertz bigger actually would be green, right? So this, if you look up what green light is, it's pretty close to green light. So you'd see it, I mean, it would be yellow light, but it appeared to be green, which would be a problem with traffic lights because you have yellow traffic lights appearing green if you're going that fast, right? So they might have to do something with traffic lights if we can ever get up to this speed. But for now, we're nowhere close, so it's fine. Okay, so the next part is, so that's how you do part A, approaching. So the next part is, what if the person was receding at the same speed? So you can picture this as, you go, suppose it's a traffic light, and you go through the intersection, and now you're going away from the light at the same speed, right? It's the same thing. So you have to use the same sort of information, but for the receding case. So the equation for the receding Doppler effect, once again, if you're not going, really close to the speed of light, would be this equation here. So it's C minus VO times C plus Vs. Divided by C plus Vs, sorry, just as I wrote it. But Vs is 0 again, because the light is stationary, right? Nothing changes. The only difference is now you're going away from that light instead of going towards it. So it's the same thing, basically, except you're just, using these equations sort of differently. So this is 5 times 10 to the 14. I mean, all the variables are the same. That's what I meant to say. So C is 3 times 10 to the 8th again. Actually, did I copy that? Yeah. So 3 times 10 to the 8th minus how fast you're going, which was 6 times 10 to the 7. Once again, divided by the speed of light, because the source was 0. If the source is not 0, you'd have to put something in here for the source. You have to add it to C. But for this case here, we did not have to do that. Anyhow, you put this in your calculator, and you get a different frequency. So the frequency is a little bit less. It should be a little bit less. And you get 4 times 10 to the 14. So it's about 100 trillion hertz less, which actually makes the light red, right? So you see a yellow light in your rearview mirror, if you're going at this speed, would appear to be a red light, right? So it's a little bit weird how that works for the Doppler shift for light. But that's basically how you use those two equations, right? It's not terribly difficult. All right, let's go back to the PowerPoint and talk about, okay, so now we're transitioning a little bit to optics. So we basically finished up the electromagnetic wave portion of this PowerPoint, and then we're going to now talk about optics, specifically this thing called geometric optics, which we'll understand what that means in a second. So the first thing we're going to talk about with geometric optics is this concept of reflection. Okay, so what's going on here is you have this thing here. Let's go back to this. So you have this electromagnetic wave, which looks really sort of complicated, right? It's basically a three-dimensional wave, which I maybe should have pointed out when I first went over it. Meaning that the electric field's in one sort of plane and the magnetic field's in the other plane. It's basically this complicated 3D wave. It's moving in some direction. So you can look at this picture, but it's sort of complicated to always figure, look at this picture to understand what's going on with these electromagnetic waves. So instead of looking at this picture here, we're going to simplify it to what's known as a ray. So a ray is basically an arrow which just represents which way the light is moving, right? So in this case, the ray would just be an arrow pointing in this direction here. So when you go back to this first thing we're going to talk about, which is a reflection, this ray, really represents this whole electromagnetic wave, but you don't want to draw the whole electromagnetic wave because it's too complicated. So you just simplify it and say you have this wave coming in, it's really a wave, it's going like this, but you can just say it's moving in this general direction here, right? And it hits some surface, say a mirror. This is an actual mirror, not some theoretical mirror, just a flat mirror. And when it hits the mirror, it bounces off the mirror and reflects. And then the wave comes off and it moves in this direction. But once again, we approximate that by a ray, so it's easier to understand. And what we can do is you can draw what's known as a normal. We did normals before when we talked about magnetic and electric flux. It's just a direction perpendicular to the surface, in this case perpendicular to the mirror. So this normal here is perpendicular to the mirror. And basically, if you measure the angle the ray comes in with respect to the normal, it's equal to the reflected ray. So this is called the incident ray. So the ray coming in is incident. That's what we say. That's the terminology, incident. Or the incoming ray is incident. And then the reflected ray is this ray. And these two angles are the same. So the incident angle is the same as the reflected angle. It's one of the simplest equations you can write down in physics. There's nothing to it. These two things are identical. It's theta I is equal to theta r, right? That's the law of reflection. It's pretty straightforward. So for flat surfaces, it's not really that interesting because this is the only case for flat surfaces. So what you have to do is, to make it interesting, put more than one flat surface together to make it curved, which we'll talk about later. We're going to have an example in a second here with more than one flat surface, and we'll see how that works. Before I do that, I just want to get into a conceptual, something conceptual related to reflection. This concept of specular and diffuse or shiny, specular is shiny, or diffuse, which is not shiny, reflection. So basically, if you have a piece of metal, metals are typically shiny. The thing that makes metals shiny, for the most part, because you can have metals which aren't so shiny, is the fact that the surfaces are relatively smooth. So if you look at a surface of a metal, it's relatively smooth and it's relatively flat if it's flat. Now if you shine light at a certain angle, so light comes in at the same angle all the time. So there's a bunch of different light rays coming in, right? So it's one wave and another wave and another wave, but they're coming in at the same angle. They all get reflected at the same angle, okay? Which means this, which means if you put your eye at this angle, you see it as a bright spot, right? Because all the light is coming into your eye, right? So your eye's here. But if your eye's over here, all the light's missing your eye. You don't see it as bright, right? This is what happens when something's shiny, right? If you tilt it, you see, it's bright, and then it goes not bright because you're tilting it so the light's hitting your eyes and going away from your eyes, right? That's why it's shiny. Now, if you have something like a piece of paper, which is not so smooth, right? If you take a microscope, look at a piece of paper, it's not smooth, right? You have all these pieces going all over the place, right? So you say, oh, okay, well, how does it work for that case? So you take the same light, right? This is the incident light, right? The same three rays. These three rays are the same as these three rays. And you shine it on a piece of paper, right? So light gets reflected off anything, including paper. It's not only mirrors. So how does it work for this case here? Well, you still have the law of reflection, but you could ask, well, how does it work if it's not flat? Okay, so if you zoom in to where the light hits, like right here, you can say this is a tiny little mirror that's angled at some weird angle, right? It's not flat because it's all bumpy, right? So this little angle, see this, where it hits here, there's a piece of the paper which is like in this direction here. So the mirror, it's not really a mirror because it's a piece of paper, but you can think of the mirror as being tilted, right? But it still comes off at the same angle that it came in at with respect to the normal. So because it's tilted, the normal is like in this direction here, as the way I'm waving my dot here. So it comes in and goes out at the same angle with respect to the normal, right? And then you look at this right here. Well, this surface here is bent the other way. It's like this direction here, right? So the normal is like this. But once again, it comes in and goes out at the same angle with respect to the normal. The point is, these are like tiny little mirrors angled at all weird directions. But it still obeys the law of reflection. Whenever it comes in, it goes out with the same angle with respect to the normal. But because these are all tilted in random directions, the light gets scattered in different directions. It's not really focused in one direction, right? So when you look at a piece of paper, it's not like shiny. If you tilt it around, you don't see bright spots all over this place. It's basically the same sort of level of brightness, no matter how you tilt it, because all the light gets scattered in different directions. So that's basically the difference between something specular, which is basically shiny. Specular is the synonym for shiny. And diffuse, which is basically not shiny, right? That's the difference between the two materials. Basically comes from reflection. All right, so now we're going to do an example of reflection with two mirrors, right? So you can't really ask any interesting questions with one mirror because the light goes in and goes out. I mean, not really that difficult. So you have to at least do two mirrors to make it interesting. So let's do an example with two mirrors. Okay, so for this case here, okay, suppose we have two mirrors that are arranged like, okay, so these are two mirrors, right? Two sort of mirrors you have in your house or whatever. And you put them sort of in a strange way, but, you know, it doesn't really matter. So you put one mirror like on the floor, and then you somehow attach another mirror to it at the end of it so that it's like this, right? So these are two mirrors. And say the angle here, though it's not drawn to scale, this doesn't look like a 60-degree angle, but suppose that's 60 degrees, right? The angle between these two mirrors is 60 degrees. So suppose you shine a light ray, right? You take a laser is the best way to think about these light rays. And you shine it on, say, the bottom mirror at some angle, which I'll give you in a second. I'll give you this angle in a second here, but let me just draw the picture. All right. So you shine it like that on the bottom ray. Just conceptually, you know, this is going to bounce off at some way. And it's going to hit this other mirror, if this mirror is big enough, which it is. And then it's going to bounce off this the second mirror like this, right? Somehow like this. We're going to get into the details how this works in a second, obviously. But just as a sketch, you know this is what's going to happen. So the question is, what is this angle here? So I measure the angle between the second mirror and the final ray after it hits the second mirror. What is that? What is that angle? Right, which I'm going to call phi. Okay, so this is known as a geometric optical problem because basically you use geometry to basically figure out the answer to this question. You'll see how this works in a minute. Okay, so let's first look at the first mirror. So draw the normals, or normal for the first mirror. Yeah, so I guess I'm going to do it step by step. Sometimes I do it all at once, but I'll do this step by step more or less. Okay. So what I mean by this, oh, I forgot to give you something. This hits the first mirror at 70 degrees, so I should give you this. So that's 70 degrees. That's another bit of information. Give it information. Okay, so this seems stupid at first because it seems more or less obvious, but for some cases, it's not obvious. So you should do this for every case, even though it seems pretty obvious for this particular case. What I mean by this is draw the normal and find the angle with respect to the normal all the time, even though the end result is going to be pretty obvious, and you might say, I don't need to do that. It's still good to do this. Okay. So what the normal means, once again, is that this line that I just drew is perpendicular to the mirror, right, at this point here. So what we need to do is find the incident angle with respect to the normal. This is what I'm getting at, right? So what I want to do is find, say, this angle. So what is this angle? If that other one's 70. 20, right? I mean, 90 plus 70 plus 20 is 90, right? That's 90, right? So this is 20. So by reflection, so that's the incident angle, right? The incident angle is 20 on that mirror. What's the reflected angle by the law of reflection? 20. So that's 20. Like I said, it seems pretty obvious here, but you should always do with respect to the normal. Figure everything else out. But like I said, it seems pretty obvious. What is this angle? 70, right? Okay, that's the first step, right? Figured out all those angles, which is pretty straightforward, right? You're just using 90 degrees, basically, to figure those things out in the law of reflection. Now what you need to do is use geometry. This is why it's called geometric optics. Look at the triangle and use geometry. All right, so what do I mean by triangle? So typically there are triangles made when you start drawing these things out. What I mean here is that you have, I'm going to just do it, hand draw it. You have this triangle, see? It's not necessarily a right triangle. Sometimes it's a right triangle. But that brown triangle, right? So there's no physics here, it's geometry. If you have three angles inside a triangle, what do they always add up to? Anyone? What do all three angles of a triangle add to? 180. So what we can do is we can find this angle, right? Let's call it theta, right? So how would you find theta? Well, theta, remember, all the angles add up to 180. So it's 180 minus 60 plus 70, or 130 is the other way to think about this, right? So if you subtract 130 from 180, that gives you the other one. This is just geometry. There's no physics here. So what does that give you? 50, right? So now that angle is 50, correct? Okay. So now draw a normal on second surface, or in second mirror. All right, this is going to get a little bit messy. I'm going to try to make the sketch a little bit bigger so I can draw more easily in here. Let's see. Okay, I think that's good. All right, so we know this angle is 50 now. Let me just change this to 50 because we know it's 50. Now you draw the normal on the second surface. This wasn't a perfect picture, as you can see. What am I going to use? I'll use this color. Okay, so the normal here, I mean, I'm just eyeballing it. I'm going to move that over, but it's kind of like this, more or less. I mean, the point is that it has to be perpendicular to the mirror, right? Something like this, right? So it's not perfect, obviously. The sketch isn't perfect. But what do you think this angle is? If it was perfect, which it's not. What color do I want to use? Let's use yellow. Does yellow show up? Can you see that? Okay, yeah, you can kind of see it. So what is this angle? I mean, it's not obviously a perfect sketch, right? But what are these two angles, the 50 and this angle here, add up to? 90 again, right? So this is what? 40. So this is what by reflection? 40. And these have to, the angle that we're looking for, and this one has to add up to 92, right? So what is phi? 50, right? So that's how you do these things. It's a combination of physics and some geometry. This is why it's called geometric optics, right? So it's 90 minus 40, which is 50. So it comes off at 50 degrees, right? That's how you do these sorts of problems with reflection. All right, let me just start the next topic. We're not going to get that far, but obviously we'll finish on Thursday, and we'll do some examples on it with it tomorrow at the review session when I post the homework. So let me just start it at least. All right, so the next thing we're going to talk about, and I'm obviously going to finish on Thursday, is mirrors and lenses. Two types of each one, and then we're going to focus on one specific type of mirror and one specific type of lens. And these are the convergent cases for both. We'll talk about the divergent cases later, but for now we're just going to focus on the convergent case. Okay, so a more interesting case of reflection is taking a mirror which is circular instead of flat. So the question is, how do we make this circular mirror? And we have to learn some sort of terminology related to the mirror. Okay, so what you do is this. There's a bunch of text here, but this is the easiest way to understand it. So suppose you take a circle, like you have a ball, like a rubber ball, right? That's spherical, right? Or circular. Let's just focus on a ball, so it's easier to understand. So a ball has some radius to it, or a circle has some radius to it, which is given by r. And then what you could do is take this ball and like slice a piece off of it. So even though you slice a piece off of the full circle or ball, it was still once part of a circle. So even though it's not part of a whole circle, it still once had a radius to it, correct? When it was part of the whole circle. So when I slice this thing off, it still has a radius associated with it, right? As if it was part of the full circle. So now I have part of a circle. If I coat the inside of this once full circle with some sort of reflective material, like a mirror, it becomes a circular mirror. But the point is, it still has a radius associated with it, and this is known as the radius of curvature, r, right? It's the radius of the full circle that the mirror was once a part of, correct? Okay. Now, we made our circular mirror, right? This is how you make it. The question is, how does it behave? So the idea is this: if you take light, which comes in parallel to what's known as the optic axis, which I'm going to explain. So the optic axis is a horizontal line that goes through the middle of the mirror, right? That's just all the optic axis is. So if you take light and you shine it in so it's parallel to the optic axis, what happens is it comes in and gets reflected off the mirror. This is just pure reflection, right? So it's a curved surface. It's a little bit weird. But it's the same thing that I talked about with the paper. So basically at this point here, right, you can draw a tiny little mirror at this point here, right? So like there's a little tiny mirror that's like in this direction here. So the normal is in this direction. And once again, it comes in at some angle and it comes out at the same angle with respect to the normal, which is like in this direction here. But it's just reflection. That's all that happens. So you just send in a bunch of rays and you just do reflection at each point. And it turns out that the light rays all cross at one point, this point here, which is known as the focal point of a circular mirror. It's basically where the light rays cross, right? If you're trying to burn an ant, right? It's like the bright spot, right? If you hold a circular mirror, it's where all the rays focus. So the focal point is very simply related to the radius of curvature. The radius of curvature, once again, is, if the circular mirror was a part of the whole circle, it's just the radius of the circle. So the focal point is just half the radius of curvature. That's it, right? So basically you take half the radius of curvature, divide it by 2, and that gives you the focal point, right? Okay, so there's one thing to point out here is this is where the light rays cross, right? So basically the bigger the radius of curvature, the further away from the mirror they cross. Basically f is the distance from where they cross to the middle of the mirror here, that's f. So if you make r bigger, the focal point goes further out, right? So if the radius gets bigger, all right, let's look at this, right? So suppose you made a bigger circle, right? So you made this circle bigger. How would it look if you cut a piece of it out? Would it be flatter or not as flat? So if you make the radius bigger, right? You make the circle bigger and bigger and bigger, and you cut like a tiny piece of it out. Would it appear flatter? if you have a bigger radius of curvature or more curved? Anyone? Let's do the converse. Suppose you made the circle smaller, right? So it gets smaller, and you cut a piece out. Would it be more curved? Yeah. So the idea is the more curved the mirror is, the smaller the radius of curvature. The less curved, the bigger the radius of curvature, right? So if you have a flat mirror that's not curved at all, what do you think the radius of curvature is, or approximately? It's got to be a big number or a small number? Big. It's got to be big, which means the focal point is way, way away from it. Technically, it's infinitely far away because there is no radius of curvature. But the more curved the mirror is, the smaller the radius of curvature, and that means the focal point is going to be closer to the mirror, right? The more curved it is, right? That's the general idea there. Okay, so the next thing we can talk about with these circular mirrors, there is math behind it, which we'll get to in a minute, is how do you form an image with these circular mirrors? So what you can do is that you can do it two different ways. One way is to approximate both the nature of the image and where the image will form and if it's magnified or not by this thing called a ray diagram, which is actually pretty good to do to sketch approximately where the object will be and how it will appear. It doesn't give you an exact answer, but it's pretty good to give you an approximate answer. So what you do is you represent the object by an arrow, right? So basically, you know, the object could be anything. It could be a cat, you, whatever. But instead of drawing a cat or a person, we just represent it by an arrow, basically. So this arrow represents some sort of object. And light rays come in, and they hit all parts of the object, and they get reflected off the mirror, and it's pretty complicated what's actually going on. So to simplify it, all we do is just look at one point of the object, right? That's it, which is the top of the object, right? That's all we're focusing on. And then what we do is we draw three what's known as principal rays coming from the top of the object to figure out where the image will be. So the three principal rays work like this. They're actually easy to understand. So one ray goes out, it goes parallel to the optic axis, right? So here's the mirror, here's the optic axis here. So one ray goes parallel to the optic axis, and we know what happens if it goes parallel to the optic axis. It goes through this thing called the focal point, right? Which is half the radius of curvature of the mirror. So this is the focal point here. So you draw a point where the focal point is, right? Because you can figure it out from the mirror. So it goes parallel, then it goes through the focal point, and then it just goes on forever. The second ray is the opposite of the first ray. So what do I mean by opposite of the first ray? The first ray goes parallel, then through the focal point. This way goes, the second ray goes through the focal point and then parallel. It's just the opposite of the first one, right? The third ray goes from the top of the object to the center of the mirror, and then it comes out at the same angle it came in with respect to the optic axis. So basically, it comes in, and then you measure the angle here, and then it goes out with the same angle with respect to the normal, right? Because it's like a flat mirror at that point, right? Where all the rays converge, which is here, that's where the image will form. So what you then do is you draw an arrow from the optic axis to where the rays converge, which is here, and that's where your image will be, approximately, right? So you can notice when you do this, if you draw an arrow from the optic axis to where the rays converge, it's opposite of this case here, which means the image is flipped over. And also the actual light rays cross to form this image, which means it's real, which I'll explain when a case of not real, so you understand the difference on Thursday. And also, it's somewhat magnified, right? In other words, if you look at the height of this arrow and compare it to the height of this arrow, they're not the same, right? This one's a little bit bigger than that one, which means it's magnified. It's bigger. The image appears bigger than the object. So we'll get into the math and what a virtual image is on Thursday. But we'll do a little bit of it tomorrow in the review session too, because there's a couple problems on mirrors and lenses in the review session. All right, so see you on Thursday.